Hi guys, welcome to lesson 18 for Calc AB. This lesson's on particle motion and total change. And as you guys can see right on your screen, you have two equations. And I want to actually do something on another page to show you guys really what's important about what you see right here. So if you were to take the velocity function and you were to integrate it, now your knowledge of integration and your knowledge of particle motion lets you know that if you integrate velocity, you're going to get back your position function. More specifically, you're going to get back your position function from b, s of b, minus s of a, right? Your final minus your initial. And then we're on the interval from a to b. So we want to just say really quickly that this is going to be your final position, and this is going to be the initial position. So all total change is taking the knowledge that you guys have for integration and your knowledge of particle motion, and we're going to move this over. We're going to take the s of a over here. We're going to add it to the other side. So we're going to have that s of a plus the total change of our velocity on the interval from a to b is going to end up equaling where we end up our final position. And so that's what this is. This is all total change is. It's pretty straightforward when you know particle motion and fundamental thermodynamic calculus part 1. I also want to say to you guys that this, you've learned, is also the displacement, right? The displacement from A to B. So when you guys learn particle motion for the very first time, you learn that displacement is your final minus your initial. So this can also give you your displacement, and that's really important to know. So if you integrate your velocity from A to B, you're actually going to get your displacement. So now all that is said and done, let's go back over to our notes and look at what you see here. So this is just saying that the initial position, and this could be x or s or whatever, plus our total rate of change of our velocity from the interval of t1 to t2 is going to give us our final position. And you guys can see again that displacement is going to be just the integration of velocity, because again, I told you on the previous page that that's just going to be s of b minus s of a. Well, if I want to integrate the acceleration from t1 to t2, I'm going to get my velocity final minus my velocity initial, and I'm just moving that over. So this is all total change is. All total change is. Now, distance, and we'll get to distance as well, but distance is going to be the absolute value of this velocity. And again, it's the absolute value of basically your displacement. So if we were to go and, travel around a track, right, and we go back to where we started, our distance traveled is going to be this whole track here, right, the length of this track. Our displacement, however, will be 0 because we ended up where we started. All right, so now hopefully you guys have a really strong foundation for total change. So let's go ahead and do some problems. So we're going to start with problem number 2. Problem number 1 is just a little blast from the past with 3-month sum. We'll do that one in another video. But problem 2 says a spider is walking up a vertical wall. At time equals 0, the spider is 18 inches off the floor. Okay, so this is really important for this problem. So this is our initial, right? So our initial position. So at time equals 0, our position is 18 inches. So I should actually say our position at time equals 0 is 18 inches. The velocity v of the spider, measured in inches per minute at time t, is given by the function graph shown to the right. So this is a velocity function. Now, some of these questions are going to be from a review from particle motion, which is actually good that we have that. So part A says, at what point in time does the spider change direction? So this is just a good little blast from the past. So I'm going to go ahead and just tell you guys, and hopefully you know these answers before I even tell you, that our time equals 6, our particle changes direction, because remember it's moving forward up here, and then at time equals 9. At time equals 6 and time equals 9. And the justification that you're going to write for this, and it's not crosses the x-axis, you're going to say that your velocity changes signs. Okay? You got to stop saying it crosses the x-axis. And you got to say velocity changes signs. That's the correct justification for this particular example. So make sure you guys are good with that for that problem. What's the acceleration of the spider at time equals 2 and at time equals 5? Well, if you guys look at the problem, remember the acceleration is the derivative of our velocity. It's our rate of change. So our derivative, and it's also our slope, right? That's how we learn. So at time equals 2, our velocity is constant, right? Our velocity is constant. So the slope of this line is a horizontal line. It's going to be 0. So our acceleration at time equals 2 is going to actually end up being 0 inches per minute squared. Inches per minute squared. Because again, nothing's changing here. And if I want to know what's going on at time equals 5, I just got to find the slope of this line. Well, the slope of this line looks like it's -1. So at the acceleration at time equals 5, it's going to be equal to -1 inches per minute squared. So this one, we're looking at simply slope. All right, we're looking at slope. We're looking at the rate of change of our rate of change. When is the acceleration of the spider undefined? Well, you guys have learned from the previous examples again that it's undefined where my function is not continuous. And basically it's the same where is my velocity not differentiable. So it's non-differentiable when it's not continuous, where this whole function is continuous, where there's a sharp corner, and we see that there are 3 places for that. So we know that this is going to be time equals 2, that's time equals 3, isn't it? Time equals 3, time equals 8, and time equals 9. And then the other one would be a vertical tangent line, but we don't have that in this particular graph. So with this right here. And so our justification just would be, that they're sharp corners. You could also talk about, that the limit as x approaches 3 from the left is not equal to, of the velocity function is not equal to the limit as x approaches 3 from the right. But we don't need to do that there. When is the velocity of the spider increasing? So this was one that a lot of people messed up on previously. So when is the velocity increasing? So guys, I always say about we're walking on this graph and we're just where do we start going up? So we start going up from 8 to 9. So where's our graph start? Again, look at it kind of like a positive slope. That's not the justification, but so we're walking, we're constant, and now we start decreasing on our hike. Well, we start walking up from 0 to 8 to 9, and then we can go from 9 up to 10, right? We cannot include 9 because, again, it's not defined there. And the justification that we're going to learn for this one is that if my velocity is increasing, that means that my acceleration is greater than 0, or my acceleration is positive. All right, so please make sure that we remember that. When is the speed of the spider increasing? All right, so when is the speed of the spider increasing? So this is when we're speeding up. All right, when are we speeding up? And so, again, a blast from the past with what we're going here. It's when our acceleration and our velocity have the exact same sign. So right here, my velocity is positive because, again, it's above the x-axis, but my acceleration is negative. So we know it's slowing down between 3 and 6. But from 6 to 8, we know that our speed is increasing because our velocity is negative, and so is our acceleration. From 8 to 9, we have a positive acceleration, which is, again, what you have right here, and a negative velocity. And so, again, from 9 to 10, we have, again, both of them are positive. And we would say that our velocity and our acceleration have the same sign, or more importantly, they're both positive. All right, they're both positive for this question. Okay, so let's look at the next. How many inches off the floor is the spider at time equals 10 minutes? So this is our total change. This is total change. So what this is asking us is that what is the position of our spider at time equals 10? Well, we have to take into account our initial, where are we, plus the rate of change of our velocity from 0 to 10. And this is the notation that you guys will have to write when you guys are solving problems involving total change. Well, we already know from the original that we're at 18 inches. We're at 18 inches. So we know that this is going to end up being 18 inches because remember S of 0 is equal to 18. And so how do we find our rate of change? Well, this goes back to our area, right? This goes back to the area that we would find. So we got to find the area of this trapezoid. We got to find the area of this triangle. And then we have to find the area of this triangle right here. That's a really bad drawing of that triangle. So I'm going to go ahead and pause the video and go ahead and write these answers in. Okay, so finding the area of this trapezoid, you're going to get that this area is 13.5 units. If you find the area of this triangle right here, you're going to find that this is going to be 3. And the area of this triangle right here is going to also be 3. So if we're actually asking to find our integration from 0 to 10 of VT dt, well, we want 13.5 units to the right. Then we went 3 units to the left, so it's -3. Then we also went 3 units to the right. So these actually balance each other out. These actually cancel each other. Because remember, this is technically to the left, so we're going backwards, so we're going to make this negative. And so our answer is going to be simply 18 plus 13.5, which is going to be 31.5 inches. So this is where we are once 10 minutes have passed. So hopefully that makes sense. Like I said, it's the first total change thing. And it says, what is the total distance traveled by the spider over 10 minutes? So total distance. Now guys, for total distance, we do not care where we started. We don't care where we started. It's asking how far did we travel. So total distance is going to be from 0 to 10, and it's going to be the absolute value of our velocity. So we do not care about initial. Don't care about it. We've actually done all the work for question G and actually F. We walked forward 13.5. We're now going to add the 3 that we walked backwards because we still traveled 3 units backwards, and then we're also going to add the 3 units that we went backwards or forwards. So this is going to be 19.5 inches. So that's the total distance that we traveled over the 10 minutes, or the spider did. Okay, so there's our first example. And again, guys, please make sure that you write your notation for this. This is what we're looking for total change. If I ask you for total distance, I need to see this right here. I need to see the integration, I need to see the absolute value, and I also need to see the dt. Okay, so that's our first video, and we'll come back and do a ton more examples in the next couple of videos. So I'll see you guys next.